Okay, let's talk about nuclear fission and fusion. The objectives are to define nuclear fission, a chain reaction, and nuclear fusion, and distinguish between them, explain how a fission reaction is used to generate power, and discuss the possible benefits and current difficulty of controlling fusion reactions. Fission reactions can release more energy than a nuclear decay reaction. When additional neutrons are introduced to an atom, it disrupts the ratio of neutrons to protons, which can result in an unstable nucleus. Fission is the splitting of an unstable nucleus into two separate nuclei. Also produced are three neutrons. This phenomenon was first observed and explained in 1938 by German and Austrian physicists. Here's an animation of nuclear fission. Nuclear fission. A chain reaction is when the products of a reaction can further react, making the products into reactants. These reactions can result in chain reactions if more fissionable materials are exposed to the neutrons produced. They can be carefully controlled so energy is released slowly and utilized to do work. If they occur too quickly, an explosion results like an atomic bomb. Here's an example of a chain reaction. The neutron hits the nucleus of one atom, which breaks into two daughter nuclei and forms three neutrons. And those three neutrons go on to cause fission in other nuclei. When heavy atomic nuclei is bombarded with a neutron, two middleweight atoms result. Neutrons and energy also result, and that is a chain reaction. This is used in nuclear power stations and bombs. So a lot of energy is produced by splitting an atom. There's a whole lot of energy holding the nucleus together. A neutron bombards this uranium-235 atom, makes an unstable nucleus, which then is split, and that is what fission is when the atom splits into two smaller atoms and three neutrons are formed from every fission reaction. Those neutrons go on to cause more fission reactions and leads to a chain reaction. Here are some more examples of fission reactions. Notice that fission reactions always produce three neutrons and then two smaller nuclides, daughter nuclides. Nuclear power plants generate energy by using controlled fission reactions of uranium. A nuclear reactor extracts energy from radioactive fuel. Fissionable uranium-235 is present at approximately 3% in the fuel rods, much less than the necessary for a nuclear explosion. The rest of the uranium is non-fissionable uranium-238. Fissionable isotopes include these. Uranium-235 is fissionable, but 238 is not. Plutonium-239 is fissionable. Thorium-232 is fissionable only with a fast-moving neutron. Slow-moving neutrons are used for controlled fission reactions in power plants. More than 100 nuclear power plants are operating in the United States. Nuclear power accounts for 20% of all electricity used in the United States. France uses most nuclear power compared to other countries. 70% of its electricity is attributed to nuclear reactors. Other fission sources. Plutonium can be used in nuclear reactors. However, during the fission reaction, more fissionable material is produced than used. These are called breeder reactors. They're very dangerous due to the ability of the produced plutonium-239 to be used in fission bombs. Health concerns. Nuclear reactors produce very little in the way of pollutants. Water vapor is the byproduct of the reaction. The radioactive waste from used nuclear fuel rods are difficult and expensive to dispose of. The risk of explosions or fires causes great resistance to building these power plants, as radioactive materials would be released into the environment. Some examples are 3 Mile Island in Pennsylvania, Chernobyl in the former Soviet Union, also Fukushima in Japan. Fukushima. Nuclear fusion is opposite of fission. Fusion is when two nuclei combine to form a larger nucleus. A large amount of energy is generated during nuclear fusion. Small nuclei combine to form heavier, more stable nuclei. No radioactive products are produced. Fusion reactions are easier to control, so the risk of explosions and accidents are decreased. Here's a nuclear fusion example. Tritium, hydrogen-3, and deuterium, hydrogen-2, fuse together to form a helium-4 atom, a neutron, and lots of energy. Two light atoms join to form heavy atoms, and energy is released. This happens in the sun, stars, and the hydrogen bomb. Nuclear fusion reactions do not occur as readily as fission reactions. They require a tremendous amount of energy to initiate the reaction. In the sun and stars, the excess pressure combined with extremely high temperatures triggers the fusion reaction. On Earth, a temperature of 200 million kelvins would be required. There are many technical difficulties associated with these types of reactions, such as a heat-resistant reaction chamber outcome must exceed input to be practical. Here's an animation of nuclear fusion. Okay, and how does fusion power the sun?